If you haven't submitted the homework yet, there's 5 more minutes, so don't forget to submit. Just hanging out a little bit. All right, it's 4:56. Let's get started. So today we are going to talk about a long promised Haskell topic, namely type classes, which will hopefully explain a lot of the weird syntax that sometimes you may have run into while you were working on your Haskell code. So what are type classes? Well, to talk about the type classes problem, it's helpful to first talk about what the problem type classes are trying to solve are. So in this slide, I have a simple example where I'm writing a function called member. What is member? Well, member takes a item and it takes a list of elements, and it basically just tests whether or not that item is in the list in question. Because Haskell is a very polymorphic language, right? We don't like repeating ourselves. We'd like to write only one copy of member that will work for any type we give it, because you want a member function that can test a list of booleans or a list of integers or a list of strings. Anything should work. So I've written out what a very reasonable looking implementation of member might be. We see, well, if the list is empty, then X is not a member of the list. And if the list has elements, well, let's check if X is equal to Y. If X is equal to Y, where Y is the head of the list, then yes, we have a member. Otherwise, we haven't found it yet. So let's just keep zipping down the list until we find something that does the equality. So this looks very plausible, and if you type this into GHCI, it wouldn't type check. And why doesn't it type check? Well, the problem is in this equality test. We've said that this function member works on any type A. And when I say any, I really mean any type A. Anything, anything, anything. It could be functions, it could be, things from outer space, and I've said, hey, it's going to work on any of these things. And like, if I give you a pair of functions, and I'm asking you to test for equality on them, well, how the heck am I supposed to do that, right? Like, what does it even mean for two functions to be equal? Do they have to, be literally the same code? Is it okay if they just always have the same behavior? ? And indeed, in Haskell, functions don't have equality. You can't actually test functions for equality. It's not allowed. And so this type signature, this signature that says for any A, I can tell you if this A is a member of some list, it's a lie, right? It doesn't work for any type. And Haskell will rightfully prevent us from doing this. And if it were just member, that wouldn't be such a big deal. But there's tons of, things you might want to try doing in Haskell that also run into this sort of problem. For example, we have the function sort. What does the sort function do? Well, it takes a list of elements and sorts them from lowest to highest. And once again, what does it mean to be able to sort anything? You might be able to sort integers, you might be able to sort strings, but what if you're trying to sort something that, doesn't have any notion of comparison? It doesn't even have to be as fancy as functions, right? It could just be some sort of data type where, there really isn't any natural way to compare between them. You probably don't want sort to work on that case. So how do I distinguish that? Or let's talk about addition. This one showed up a lot when I was doing very simple examples, right? Addition, well, you want it to work on integers, you want it to work on floats, you want it to work on doubles, you want to work on all sorts of numeric types, but you don't want it to work on, some random, colors, right? Like, what does it even mean to add, red, blue, or green together if that's just your enum? And, strings, well, Haskell said, no, you can't add strings together. You need to concatenate them instead. We've talked about show. Show is that handy dandy function that lets you take any value and turn it into a string representation for itself. But sometimes you just can't, produce a string representation like functions, and it won't work in that case. And there's also other things that we haven't seen. For example, if you want to serialize some data onto disk, you need some recipe for saying how things should actually be laid out. And once again, you can't assume that's going to work. And similarly, we've talked about data.map. You've used data.set actually in one of the labs, and I mentioned how that was implemented as a binary tree. So you need to compare things. But Haskell also has implementations of good old-fashioned hash tables. And well, to have a hash table, you need to actually be able to take some element and compute a hash code from it. And well, how do you do that, right? Sometimes it's not possible. So this sort of idea where there's like a bunch of types that have some property, have some behavior that work for them, but not all types. And this shows up all over the place, everywhere. And so it's a big problem. And originally, when Haskell was being developed, it wasn't at all clear how they were going to solve this problem because there were a bunch of solutions, but they weren't very satisfactory. Let's take a look at a few of them. So one solution, which which I'm calling non-local choice, the idea is when I say multiply a times b, what I'm going to do is I'm going to look at what the types of a and b are. So if a's are integers, then that just means when I say a times b, actually what I meant to do was call some special function multiply integers between a and b. And similarly, if I look at the types and I say, oh, this is a float, then I'll do multiply float instead. And this works okay if you write standard ML. Actually, that's exactly how they handle the arithmetic operators in that language. Those of you who write C++, this might look very familiar because it's very much like overloading, right? How does overloading work in traditional object-oriented languages? You look at what the types you're given are, and then you use that to select the most specific overload for your function in question. And so this will work okay if you have 3 times 3 or 3.14 times 3 times 14, but there's a problem with local choice. And the problem with local choice is that it is not compositional. So let's imagine that I've got my multiply, and then I want to make a function that uses it. Let's call it square, right? What does square do? It takes a variable and it multiplies x by itself. And so the problem that I have in this situation is I would like to select exactly what the multiply is going to be, but I don't know. In Haskell, I would want square to be some sort of polymorphic function that would work on both integers and floating point. But if I'm just looking at what the types are inside the body of the function, I don't know what it is if I have a polymorphic function, right? It could be any type. It could be integers, it could be floats, whatever. So if you were writing this code in standard ML, you would have to actually give this a monomorphic type signature for the multiply to work out, right? To say, hey, this is actually multiply on integers. And now I don't get a polymorphic square anymore, right? I have a square that works on integers, but not one that works on floating point numbers. To put it differently, this concept of non-local choice is basically the language cheating and giving like some specific identifiers like multiply or plus, some special property that sort of they know how to look at the types and figure out what you're going to do. But this capability didn't extend to users of the programming language. And so although the compiler is like, I've got mine, haha, too bad for you, you, the user, can't actually make use of the same facilities that the compiler gave you. Those of you who are familiar with C++, in C++, this is resolved in a different way. Namely, you actually just stamp out as many copies of square as necessary whenever you do a template instantiation. If that didn't mean anything to you, it's okay. We're going to talk about C++ and template programming in excruciating detail. Well, okay, not excruciating. Well, we'll talk about it in more detail once we get to the object-oriented portion of this class. What are your questions so far? I see someone saying templates are the best. There's a question, why is this a non-solution despite other real languages using them? Yeah, that's a good question. So it's a non-solution in the sense that Haskell did not choose it. And also, and here I'm going to put on my sort of opinion hat. My opinion is that this is not a good solution. And like if you were designing a language from scratch, you should try to avoid doing this sort of thing. Okay, so oops, I've gotten ahead of myself. So this slide is just recapping what I said about C++, which is that in C++, this non-modularity is solved by stamping out multiple copies of code. So I already mentioned one of the downsides of doing this, which is that you have to produce multiple copies of the code in this situation, and in fact, you can end up with a so-called exponential code blowup, right? Where if you like implement square xy, which is just squaring x and squaring y, then I have to do a copy of square xy for every permutation of the types of x and y here. So C++ gets a sort of reputation for taking a very long time to compile, and part of the reason for that is this exponential code blowup in this situation. There's also another problem with the C++ implementation that I haven't mentioned here, which is that in C++, type checking gets deferred until you actually instantiate it. So if you're writing a template function in C++ and you write it wrong, you won't actually know until you try instantiating it with it. That's not true in Haskell. In Haskell, you'll find out if you did something wrong when you are writing your polymorphic function, which maybe you've already noticed when you were trying to write polymorphic functions in your code. Okay, so let's look at another non-solution. So this non-solution is whenever we have one of these functions, let's provide it for everything. So let's just imagine that we need an equality in our language, and yeah, it doesn't really work on everything, but we really, really, really want equality. So we're just gonna say, okay, we're gonna make an exception. Equality is a magic function, and it works on any type, even though it doesn't make sense. And we'll just say that, hey, like if you try to test equality on integers, great, no problem. And otherwise, runtime error. There's a question which is the lecture being recorded? And the answer is yes on Twitch, but not on Zoom. So let me get Zoom zooming. So thanks for reminding me. Honestly, we're already missing a bunch of recordings in Zoom. So if you are trying to catch up on lectures, I just recommend going to the YouTube videos instead. Okay. And so integers, it'll work fine. And then I was like, hey, what am I going to do if I have functions, right? Well, I could, make up something random. I could have it raise an error, something like that, right? So the idea is I'm just going to like try to do something in this case and pray. So hopefully it kind of makes sense why this is not such a savory solution instead, right? So one is it's not extensible. I did this for equality. What if you come to me and you're like, hey, Ed, I also want to be able to do comparisons in my language? Well, then you have to actually go to the compiler and, beseech the compiler to provide you, some like all of the things you actually need. And that's just a really bad place to be in, because the compiler typically wants to move slowly. People take their time upgrading new compiler versions. You really don't want to be waiting for your compiler to get a feature like supporting ordering comparisons on your data types. Also, in Haskell, we're big believers in using very precise types, right? So like we said, when I want to get out what the head of a list is, head in Prelude was a mistake. That one raises an error, right? And there's no way to recover from errors inside pure Haskell. But if you do something like this and you have a to bool and you say function equality is a runtime error, well, like now you've got errors, ubiquitously in what I would call a very core part of your programming language. And finally, this is abstraction violating, right? Like, because if you have some, type that you've created on your own, like some sort of custom user-defined data type, how does Haskell know what equality on that user-defined data type is? Well, it doesn't, right? If you said, hey, the programming language magically knows how to do equality on everything, then there's only really one way it can implement equality, which is to look at every field in turn and do an equality test on each of them one by one. But what if you're writing some sort of data structure and maybe there's a bunch of equivalent formulations for the same thing, and you don't actually want to require exact structural equality? Like, say you're comparing two sets and they're represented as binary trees. Well, the sets should compare as equal so long as they have the same items. And I don't care if the internal balancing is slightly different. But if I force my compiler to provide equality on everything, then there's no way for me to say, but wait, I want something different for my particular, I want to be a little more abstract. We'll talk about abstraction, by the way, some more when we do modularity as a later lecture. But in short, I want to be able to hide some details from other people. And when you look at this sort of situation, it's not at all clear how to prevent the compiler from seeing everything in your definition, because the compiler said, yeah, I'm going to figure out how to define equality and everything. And it gets even worse, right? If you're talking about ordering, how the heck are you going to do that? Lexicographic on everything? Well, that probably isn't right in some situations. Okay, so so there was another idea which was proposed early on in Haskell's development, and this was this idea of an eq type. So what's the idea behind an eq type? So earlier I said, hey, equality is cool, and there are lots of types that know how to do equality, but not all of them. So what if we added some sort of annotation to our type system to help us, figure out when types could be equal or not? So in the sort of made up syntax here, what I've said is, okay, so equality isn't a to eta bool, right? It isn't give me any type variable a and I will give you a Boolean saying if they're equal or not. Instead, give me one of these special equality A's, where equality A's are only allowed to be types that support equality. And then I can write my member function, a, which says, hey, give me any A as long as it's one of these equality types. And then, there's an obvious question, which is, hey, what about everything else, right? So you built in equality into the type system, but I gave you, 6 examples of all sorts of other situations where you might want this. So you'd want to somehow make it so that this was user extensible. And thus were born Haskell type classes. And I kind of am presenting this as a fait accompli, but when Haskell was being developed, they were really trying to figure out what to do about this. And Haskell was originally formulated as a committee language. They wanted to sort of do some very conservative, best of all the lazy functional languages that were being developed, so people would just start doing research on top of it. And when they got to this point, they were like, oh my God, we need to actually come up with something new, something that we've never done before to make this work out in the language. And fortunately, they decided to take the risk, and that risk is type classes. Okay, so how do type classes work in Haskell? So it's very similar to eq types, except that we've just generalized it. So instead of having some sort of special syntax, we're just going to say there's this concept of type class. And when I say some type A has a type class, what I'm saying is that, hey, I'm going to accept this code for any type A, provided that A is of type class num. So now we can actually look at the signature and understand what it says. It says, square is a function that takes A's and produces A's. And these A's can be anything so long as the A as a type class num. And I've said type classes need to be user extensible, so these type classes are all defined inside the language. Of course, there are a bunch of type classes that are built into the standard library, but you as a user are also welcome to define your own type classes and give them names and then refer to them in constraints inside of your type signatures. And of course, we can see this pattern play out in a bunch of other examples. So for example, we have sort, right? So what does sort say? It sort says, I'll take a list of A's and give you a list of A's so long as the A is of type class ord, where ord means these are ordered types. They have some notion of comparison. Or show or serialize says, hey, given any type A, I'll give you a string so long as A is of type class show, which is the type class that says, hey, I can actually print myself out. By the way, if you remember when we did the algebraic data types lecture, I defined an algebraic data type, and then I wrote this deriving thing that said, deriving show, which just made it possible for GHCI to print it. And what that did was basically defined a show instance for the type that we were just defining, so that when I used the type in functions like this, it would actually have a show type class. So A is of that type class. And finally, our main example member, A simply needs to be eq, where equality is defined on it. Haskell distinguishes ord from eq because some types have equality and some types also have ordering, but some types have equality but not ordering. So in that case, you would have an eq instance but not an ord instance. There's a question, which is what type classes are derivable? And I don't know off the top of my head, but actually show, eq, and ord, they are all derivable. And this kind of makes sense because they have very sort of regular implementations, right? Equality, what is the derived implementation of equality? It just tests that each of the members are equal. And of course, you don't have to use deriving, right? You can also write the instance by hand, and that solves that other problem, which is, how does the compiler know when it should ignore some internal details? Well, if you need to ignore some internal details, you just write your type class by hand. There's also some advanced features where you can actually teach the compiler how to derive type classes that it doesn't even know about. Deriving used to be a compiler-only feature, but it's also something that can be programmed from users. Okay, so we're going to hop to GHCI and take a little closer look at some type classes. Okay, so we're going to first take a look at some of the basic type classes in Haskell, and we'll use this as an opportunity to look at the different parts that make up a type class. So I mentioned show already, and if I want to know more about show inside GHCI, I can do :info show, and it'll give me a bunch of information about how show works. So let's scroll up a bit and see what's going on here. Maybe I shouldn't have done show. Let's do eq. Eq is nicer. Okay, so there's a bunch of stuff here, and we need to scroll up, and here's what's going on. Okay, so what is equality? So equality is a type class. So a type A has type class EQ, and when it has type class EQ, there's now a bunch of functions. And what these functions say are basically what are the so-called methods that are defined on this type class. So in equality, there are two methods defined on the type in question. One is equals equals, which takes two A's and tells you if they're equals. And the other one is not equals, which takes two A's and tells you if they're not equal. By the way, there's this little annotation. It's not important, but what it's basically saying is if you want to define equality, you only need to define equality or disequality, and the other one can be automatically inferred. After that, we have a whole bunch of instances, and what this is basically just saying is all of the type classes that support equality. So let's ignore this one for a moment. You can test for equality between words, byte unsigned integers. You can test for equality between ordering. That's an enum that basically has three members, LT, GT, and EQ for the various comparison situations: integers, floats, doubles, all the things you would expect. This line says that something interesting, which it says you can test for equality on lists as long as you can test for equality on the elements in the list. So this double arrow, we've seen already on the slide very briefly, which said, I've got a function, and this function works so long as the type in question is an A. So it's kind of implication. If this holds, then this also holds. And that also applies here with the instances. It says if A is of type EQ, then list of A is also of type EQ. So this explains some of the types that we might have seen. So like if I ask for what the type of equals is, we see, hey, this is a function. It takes two A's and produces a Boolean so long as A is of type EQ. And let me see. So for example, show, this other example says, A can be converted into a string so long as A is of type class show. And so now I can finally explain the error message you get when you do something like this. So I typed in a function and I asked GHCI to print it, and I got an error. And what this error says is no instance for show P0 arrow P0 arising from a use of print. So once again, why is there a use of print? Well, I didn't explicitly say print, but GHCI will implicitly attempt to print anything that it is, returned from inside an expression here. So what exactly is the thing that I'm trying to print? Well, it's this lambda function that takes x to x. So it is a function of type P0 to P0. And GCI is saying, hey, I can't print this because there's no instance saying how to show functions. And now, hopefully, this error message seems very reasonable, right? I tried to print it. I couldn't print it because there's no show instance. Hooray. And of course, if I do something very normal, then I can get a number 2. There's a question from Twitch, which is it accurate to say Haskell duck types the object? And there's actually a very precise answer to this, and the answer is no. So just for those of you who don't know what the term duck type means, duck typing refers to this idea that if it quacks like a duck and it walks like a duck, it is a duck. That is to say, there's no need to actually declare something to be a duck, so long as it implements all of the behaviors a duck expects, you can treat it as a duck. And in dynamically typed languages like Python, duck typing is very common because there's just no way to actually declare something being a duck. So, you pass something in, most of the time people are just going to try to call methods and fail if you don't. In Haskell, that's not the case, right? So, there's a few things going on. So one is that I can't actually, define the thing. I can't redefine show. Show is a function, right? I can't do my own definition of show. If I did, I'd just be shadowing the type class show. But second is that I have to explicitly declare any given type as supporting show for it to support show. So I'm not allowed to skip that step where I say, yes, this is indeed a duck. So it's not duck typing. Another question from chat, why is info only listed for tuples up to length 11? Does that mean tuples containing eq types of length more than 12 are not a length eq? And let's just try this out. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And let's just test for equality against itself. That's my kid in the background. And this did indeed work. And so I think there's some just sort of printing thing going on where I don't remember how this works. Tuples are a bit funny how they're implemented in Haskell. So there is a limit. You can only go up to 64 size tuples. If you want more than that, you should just make a friggin' data type. But yeah, equality does work on them. So I don't know why the instances don't get printed. Okay. All right, there's one more example which I want to show, which is I worked very hard not to do something like what's the type of 2. And so now let's take a look at this. So this is very interesting. So Haskell's telling me that 2 has the type P. So it's any type. Hooray! Like, cool. I can use 2 anywhere I want. Maybe? And except no, there's a constraint, right? P has to be some sort of numeric type. So let's take a look at what num is. So num is Haskell sort of grab bag type for anything that's vaguely numeric looking. The most important thing about it is that anything that is an integer can be represented as a num. And we see that num implements a bunch of operations like addition, subtraction, multiplication, and there are a number of types that support num, like the integral types as well as the floating point types. And so why does 2 have such a strange generalized type, right? Normally you'd be like, well, 2 is just an integer. Why don't you just say 2 is of type integer? And the reason is that when I have a polymorphic type like this, I can simply use the same literal, but in different situations have it either be an integer or a float. I haven't committed to what the type of the number is yet. So the 2 can just take on whatever type I want it when I need it. So those of you who are familiar with C-style casting rules may know that in languages like C, this also kind of works where I can add 2 with a floating point number and I'll get a floating point number, and I can add 2 with a integer and I'll get an integer. And in C, this functionality is implemented differently. It's implemented by something called type integer promotion rules, where when I do a mixed operation like adding integers with floating points, there's some rules by which some of the types get converted into different types, and then the operation is carried out. In Haskell, that is not there's no such thing as integer promotion. So for example, if I try to add an integer and a floating point number together, Haskell will say, hey, this doesn't work. Addition, and let's remind ourselves what the type for addition is. Addition takes an A and then another A and produces an A, where A is some numeric type. So importantly, these A's have to all be the same. So I can add 2 integers together, I can add 2 floats together, but I can't add an integer and a floating point number together. So the only reason why 2 plus 2.0 actually works is because 2 is not actually an integer. It's some weird, P type where P is some num, and then at the time when this addition happens, GHC says, oh, actually this needs to be a floating point number at this point. This can be kind of annoying sometimes if you're used to getting lots of implicit promotions, but a lot of people like it because it also makes it more difficult to accidentally, do an implicit conversion that you weren't intending to do. And oh my God, C implicit conversions can really mess you up when you are doing them. Okay, so that's enough about some of the type classes that you've already seen while you have been working on your Haskell labs. Let's talk a little bit more about how we define type classes. So to do this, let's just try redefining one of the type classes that is in the basic library. Let's talk about equality, for example. So we're going to call this myEq because the name eq is already taken for equality in the standard library. And how are we going to do this? There's a question in chat, which is, wasn't C++'s explicit keyword designed to combat implicit conversions? And the answer to that, okay, so I'm gonna assume you know what explicit means. I am not going to explain what explicit is. So if you know what explicit is, explicit will let you avoid implicit conversions from constructors. But the integer conversions, for example, they always happen. There's no way to turn them off unless you do funny business with templates, because templates impede implicit conversions. So you can get it to not implicitly convert in that case. But other than that, yes, you can avoid implicit conversions in some situations, but in other situations, the language is just going to go ahead and do them for you. You can't stop it. Okay, so we're defining this type class myEq, and we're going to sort of follow the outline that we saw before, which is we have we have a bunch of, we've defined our type class. And once we define our type class, we need to say what methods are on it. So the way to think about it is when I'm defining a type class, I want to define some operations which are always available for any type that is of this type class. So I need to define what those operations are going to be. So for equality, it's very reasonable to want to be able to test for equality. So hey, I need to actually have some method named EQ, which takes two A's of this type class and tells if they're equal or not. So once I do this, I can ask what the type of EQ is, and we see that the type here doesn't match exactly the type that I wrote in the file, and hopefully this makes sense. So when I am writing methods inside of a type class, I implicitly get to assume that, well, the A is of myEq, right? Because that's what I'm doing. But when I'm in here, when I'm asking just what the type of EQ is just a free floating function. And well, you better give it something that is myEq in the situation. Okay, so let's go ahead and try defining an instance. So we might try defining an instance on integers. So to define an instance, instead of using class, which defines a new type class, we say instance myEq. And then we provide the type that we want to define an instance for. So this is saying, hey, integers are of type class myEq. And to define an instance, I need to give definitions for all of the methods in the type class in question. If I don't, a Haskell will complain saying, hey, you didn't give me an implementation of equality. Well, actually, it's saying no explicit implementation for EQ, and that's because something very funny happens, which is that it'll automatically fill in a default implementation if you don't give it anyway. That's you can turn this into a hard error. Warnings in Haskell are very useful, and I recommend actually looking at them because sometimes things are warnings and they shouldn't be warnings. They should just be errors. Okay, so we need to define this function. So what exactly is going to be the type of this function? Well, in the type class, we wrote eq as saying it works for any type A and any other, and A to bool. But of course, when I'm actually writing an implementation, I want to specialize A to be some specific type. There's a question in chat, which is int a type class too? And the answer is no, int is not a type class. Int is just a type. So when I write equality, I get to replace all of the A's with integers. So I just need to write a function that takes two integers and tells me if they're equal or not. And so a really crappy implementation would be like something like this. This is a really crappy implementation, but whatever, right? We're just writing things. I'm technically not allowed to write these because it's always clear from context what the type of eq is, because the type is precisely whatever this type is with a substituted to be int. But there's a language extension that lets you write it explicitly. Language extensions. GHC is so helpful. It'll helpfully suggest what language extension you need to make something work out. So usually if you just listen to it, it'll work. By the way, what's going on here? So what's going on here is that I got this ambiguous type variable warning. And the reason this happened is because when I write an literal, I'm not actually writing an integer. I'm just writing, this is something of type P where P has instance not. And so Haskell's like, hey, I don't know what actual type you wanted because you fed it straight into another type class, which also doesn't tell me what the type should be. So I need to explicitly say this is an int. And then hooray, it'll tell me 0 equals 0 and 0 does not equal 1. And of course, it'll tell me 3 does not equal 3 because, well, I didn't code it, but that's okay. In the standard library, right, there's an actual implementation that knows how to actually do primitive integer equality, and we don't have to care about that. This is just for examples. Okay, so let me see. What do I want to talk about next? I've got time. Any questions so far? Okay, so let's look at a little more interesting type class. We'll call this MyNum. So MyNum is going to represent types which have sort of like numbery properties. And for this particular example, I'm going to say, well, numbery things should support addition and multiplication and negation. And this looks very much similar to the equality type class, but of course I can write as many methods as I want. Right, a type class is not obligated to only have one method. It can have as many as you want. And another interesting thing is this type class says, hey, give me 2 A's and I'll give you an A back. And this should be kind of shocking to those of you who have written Java, where this is actually very difficult to do with Java's sort of equivalent functionality interfaces. And we'll talk a little bit more about that when I go back to the slides after the GHCI session here. So I've written a bunch of methods, and of course, when I want to actually implement this on some type, I just have to define all the methods in question. And I need some plus int implementation for this to actually work, and multiply needs some actual mult int implementation. There's 2 questions in chat. So the first question is, do we usually define instances where we define type classes or where we define types? That's a great question, and it's actually a very deep and interesting problem. So let's say that you're defining a new type. We did data, colors equals red, green, blue. And I might very reasonably want to do equality on this. So what I will typically do is I'll write the equality instance right after I do the implementation. Or really, because equality is derivable, I'll just derive the instance directly. However, let's say I'm writing a new type class like my super serializer, which is a very efficient, let's suppose, serialization implementation. Then what I'll typically do is once I've done this, I'll probably want to write instances for a bunch of standard library types which were already defined. So the answer to your question is it varies, but typically if you define a new type, you're going to define all the type class instances that make sense for it. And if you define a new type class, you're going to go ahead and define instances for all the standard library types which you want your newly defined type class to work on. There's another question, which is where can we see the standard library implementations of things? That's not an easy question to answer, but let me see. Let's pop open Firefox. So going over to trusty old Google. So how do I do this? Okay, so Google is going to take us to the standard library documentation for addition. And will this show me instances? Yes. It'll very nicely give me a bunch of instances that num is defined on. So if I'm curious about what the actual internal implementation is, I can click on this source associated with the instance, and I will see this, which is the internal int8 implementation for num. And there's a bunch of random crap which is kind of hard to read because I haven't told you what any of this means. The short answer is inside of a int8 there is a unboxed int8, and then there are a bunch of intrinsics which are defined directly by the compiler for doing unboxed computation on it. Unboxed types are the keyword if you're curious about what these hash mean. But yeah, that's a very nice way. It's very easy to look at internal details from the Haskell documentation. So I highly recommend looking around here if you're interested. Okay, so back to the file. This isn't going to type check, so let me just comment it out. So we got our MyNum type, and I just want to emphasize how this solves some of the problems that I mentioned in the slides. So for example, I had this square example where I where I said, hey, I want to implement square by simply multiplying x with x. In fact, I don't even have to write the type signature, and Haskell will be able to figure out what the type of this should be. The type of this is, hey, I can take any type A and produce an A so long as it's a num A. And why is that the case? Well, what's going on internally is Haskell looks inside and says, hey, you use multiply on x. Multiply adds a constraint saying that x's have to be num, and that's the only constraint, so you're pretty good. So if I do something funny like show square, where I multiply x by x and then I show it, I'll get a different type. And what's this type? Well, hey, this is something that we haven't seen before, but hopefully it is intuitively clear what this says. This says, hey, this is a function that takes a's to strings. The a has to be numeric because, hey, we multiplied it. And the a also has to be showable because, we're going to try printing it. So there's now 2 constraints on a. In fact, you can have as many constraints as you want on as many type variables as you want inside a function. You're not limited to just saying, num a to a to a. So going back to the square implementation, right? I only had to write one implementation. I only had to, I get a single function. It is compositional, right? Just like the multiply operator had a num constraint, the square operator also has a num constraint. I can build as big a thing as I want. And in fact, when I compile this, Haskell does not need to duplicate this for every implementation. In fact, there's a way to to compile this into a single function, and we will talk about that very shortly. Questions? Okay, I want to go back to the slides for a moment, and then we can look at some more interesting examples in a little bit if we have time. Okay, so let's just recap what I said here. So as I said, if I define a type signature, everything to the left of the double arrow equals greater than specifies what constraints I have on the types in question. So I can have a polymorphic type with this lowercase type variable saying it works for any type so long as it is a type instance num. And when I want to define new type classes, I write a class blah where I say what are the operations that, if I want a type to have this type class, that type has to support. And then I can write an instance declaration, which says, hey, how do I actually implement all of the operations on the type in question? If you're looking at the keyword class and you're thinking to yourself, oh, are type classes like object-oriented classes? The answer is no, not really. Don't. It's an unfortunate terminology collision, but it's most helpful to just think of these as their own thing, not at all similar to object-oriented classes. Okay, so I promised I'd tell you how we actually compile type classes, and in particular how we avoid having to stamp out multiple copies. And so the way type classes work is via a thing called dictionary passing. But before I do that, there's a question. So the question in chat is, what if I wanted to find star for something that doesn't really fit what a num is? And the answer to that is actually, that's a really great question. And there's actually lots of situations where you might run into something like this, right? Like, for example, you might be a big fan of the Python syntax where if I multiply a string by a number, I get that string repeated that many times, right? And you might be like, that's so cool, I want to do that in Haskell. And so the answer to this question is basically don't do that. In more words, when someone, defines a type class, you're supposed to only define instances of that type class that are morally that type class in some sense. So think about the type class as a way of sort of organizing, the meanings of types, not as a way of getting at, a operator that you really wanted, right? Like if you really, really want the star operator to mean something else, you have the option of basically throwing away the Haskell prelude, saying, hey, don't give me num. I want to define star to be my own thing in my own type class, and then you can go off and do your own thing. But Haskell makes it easy to define other infix operators. You can define as many infix operators as you like. Some people really don't like this about Haskell because it's hard to search for infix operators. Although, remember, you can search on Google. Google understands symbols and will be able to find them. And so there's a lot of custom infix operators in Haskell which do various things that, wouldn't necessarily, like you don't need to redo star. You can get your own thing. And we'll talk a little bit about monads soon, and they have their own syntax, and it's directly implemented this way. There's another question, which is, so we can't really operator overload in Haskell? And the answer is yes. There is no operator overloading in Haskell. So star can work on different types, but that's because it's part of a type class. And so you have to implement an instance of the type class to change the behavior of star. You don't get to say, oh, and I also want string times int to do something else. That's not allowed. Okay, so let's talk about how type classes work. So, where to start here? Actually, let me answer this question. So there's another question in chat, which is, could I repeat what we should think of type classes as? Why not as a means to achieving a specific operation? This is a good question. So I guess I should walk back what I said just now a little bit. Why do we write type classes? Well, so I mentioned earlier that one of the reasons why we write type classes is we want to write functions that are polymorphic, but only work on certain types that support some sort of operation. But it's true that another reason we write type classes is because we want to use one operator name and have it work in a bunch of situations, right? Like, so they're kind of two sides of the same coin. The reason why I can say 2 plus 2 and 2.0 plus 2.0 is because plus is part of a type class. And that also means, like, so yes, now I can write polymorphic code that works on arbitrary numeric types. That's cool. But I also get to reuse the same operator in different contexts. So like I get both of these things, and they're both useful. What I meant to say earlier is that you should just be careful about only defining type classes just because you want to reuse an identifier in multiple contexts. There should be some sort of, the way we like to say it in Haskell is there should be some laws. There should be some, like rules that say when something is the type class or not. It's not just a way of reusing syntax. There should be some underlying semantic meaning behind it. And it's maybe a little difficult to see what I mean by this right now because all we've done so far is look at sort of very bog standard classes. But when we talk about monads, you'll see what I mean by laws, because monads are this very abstract thing. It's very hard necessarily to understand when something is a monad or not. And so in those cases, we will actually figure it out just by thinking about what the laws are in the situation. So there's a question which is, follow-up, which is it kind of like a relation among operators? They're related, I will say that. I'm thinking relation in the sense of relational databases, and I'm not exactly sure that applies here. Okay, so how do type classes work? So on the left-hand side, I have a traditionally written type class where I say num n, double arrow, and end to n. And you're supposed to read that as my function really is end to n. And there's a constraint saying that n has to be numeric. And so what I'm going to tell you is actually, under the hood, the way Haskell implements type classes is by desugaring these constraints into function arguments. So let's unpack what I mean by that. So first of all, what do I mean by desugaring? So when I say desugaring, I mean when I'm talking about how a language feature is implemented, sometimes I can understand how it's implemented by sort of decomposing it into simpler language features. And the way this works is I have this fancy language feature. I say, hey, every program written with this language feature is equivalent to this simpler program written without this language feature. And if I can define this translation, if I can define this so-called desugaring in all cases, then I'm actually done. I don't have to go and edit the compiler I just need to understand what the desugaring does, and then there's nothing else I have to do. That defines the semantics of my program entirely. So type classes can't exactly only be implemented with desugaring because of this thing called instance resolution. But once you've figured out what the instances are, indeed, desugaring is a very good way of understanding how this code gets compiled. So let's go back to this. And so what I said is whenever I have this constraint, I'm going to desugar this into an actual honest to goodness function argument. So now num is no longer a type class, it's some sort of record. And in fact, the record represents a vector, a record containing each of the actual functions that implement the operation on question here. And so when I look at the implementation of Square, I see, okay, I take an actual argument. We call these dictionaries because the dictionary tells us how to do the various operations. And then something interesting happens, which is that what I do is this dictionary has an implementation for multiplication. So I project out the value from the dictionary, and then this gives me a function which I then can pass the arguments to. Pedagogically, this is a little confusing because I'm using the infix operator. And so the other thing to note is that in the left universe, the type class universe, star is just like a function. In the right universe, star is a record selector. It pulls out a field from the record. If you don't remember the record segment from previous lecture, a quick reminder. Right, in Haskell, we can define records. I'm going to define one right now. Oops, here we go. Data my eq d. And when I define a record, I have to put a constructor, and then I can name all of the fields on the record. So I'm going to say, let's comment this out for a moment. Eq d. The record eqd, the dictionary for equality, contains a single field, and that is a function that takes a to a's to bools. And this is a valid Haskell program, and it's also equivalent to if I hadn't written the field name at all. But remember, type classes can have lots of fields in them, so it's helpful to actually give names to them. Questions here? So recapping what I just said, when I define a type class, this desugars into a data type declaration. So I take my type class and I instead define a data type with a single constructor and which has fields for all of the methods that were on the type class in question. And the operators, the actual methods on the type class, are now selector functions which take out the relevant field from the data type that I've just declared. And I wrote them separately here, but as I said, if you use the record syntax in Haskell, it'll do it all for you in one go. You don't have to do it one by one. Okay, so all right. So that's it about dictionary passing style. Although I might want to talk a little bit more about it at the end of the lecture. Certainly, your homework is going to be all about dictionary passing style. You're basically going to take some type class programs and turn them into dictionary form. But I just want to talk a little bit more about some of the cool implications about type classes. So we've already spent some time in our labs looking at quick check, which hopefully has been a pretty cool and interesting testing concept that you haven't seen before. Well, quick check relies heavily on type classes to actually work in its implementation. And there are two things that are going on here. So one is that to actually quick check a program, we need a way of randomly generating data that is of some type, right? Like when you were working on lambda calculus, there was a given quick check instance that could randomly generate lambda terms. And of course, the only way QuickCheck could do that was by defining a new type class called arbitrary, which basically says how to generate random instances of some type. There's also testing functions, which is when you were writing your QuickCheck programs, you actually may have noticed that you didn't have to restrict yourself to only taking one argument. You could, in fact, take as many arguments as you wanted, and QuickCheck would figure out how to randomly generate inputs for all of the arguments. And this is also done using a type class. Namely, QuickCheck says, well, any a testable function, one you can pass to the QuickCheck function that actually, does the randomized testing. Well, if you just give me a Boolean, that's certainly testable. I'll just see if the Boolean is true or not. And furthermore, if you give me a function where A is something that I can randomly generate and B is something testable, the result is also testable. And that's how multiple functions work. You basically, keep looking up the instances until you get to the end, and then you have a Boolean and you say, hey, that's testable. Okay. I promised to say a little bit more about how type classes compare to object-oriented programming, and a very logical comparison in this situation is to compare a type class with a interface in object-oriented programming. And the question is, what's the difference between defining a type class that says how to show strings and an interface that says, hey, this is an object and show is a method on the object that returns a string. These look very similar, and indeed, when we think about what problems are being solved here, the problems that type classes are solving are very similar to the problems that interfaces in object-oriented programming solve. So there's one big difference, and the most important difference between interfaces and type classes is how dispatch is done. When I say dispatch, I mean, how do I find out what the actual code I want to call is? Haskell's type classes follow what I say is type-based dispatch. That is to say, once I know the type of A, I know what implementation I want to go to. So when I call show on an integer, I know that I want to call the implementation of shows on integers and not anything else, not floats, not strings, nothing like that. In object-oriented programming, when I call the show method on an object, I need to know what that object is at runtime to actually do the show implementation there. Because even if you gave me, say, a fruit, it might not actually be a fruit. It might actually be an apple at runtime. And so when I call show on the object in question, I will get the apple's implementation of show, not fruit, which is the type. Well, this is a little hard to see in some sense because Haskell doesn't have subtyping in the same sense that object-oriented programming languages do. But suffice to say, even if Haskell had subtyping, type classes would still operate by looking at what the type you saw was at some site. So there's some important implications to this. So for example, here is a very interesting function that is kind of difficult to do in an object-oriented programming language. So this function says, hey, give me a string and I'll produce some value. And what is that value going to be? Well, it's going to be, I'm going to take the string you gave me and I'm going to read it into some value. So I'm going to parse it into a value. And then I'm going to add 2 to it. And when I write this in Haskell, I only have 2 constraints that I need. I need to be able to, read the string into a value. So there's a standard library type class called read that is sort of the inverse to show. And then I need to do addition. So I need A to be some well-behaved number type. So think for a moment how you would implement this as a function in an object-oriented programming language. And the answer is you'd run into a lot of trouble. And the trouble you'd run into is you'd be writing your function and the function would take a string as an argument and then you'd be stuck. You'd have to somehow specify what you wanted the return type to be. And there's no, normally when you are writing functions, you would pass in the object as an argument and then you would call methods on the object to actually go ahead and do the operations in question. But there's no object argument to this function here. So you probably have to go and like add an extra argument saying, hey, this is a class object representing the class that I want to represent. No need to do that in Haskell, because when I desugar this code into a dictionary passing style, each of these constraints turns into an argument. And these arguments have the actual implementations, the records of the method implementations that I need to actually do the reading and then do the addition. So I feed in the dictionaries, which say how to do the operations, and I get the value out. And so I'm perfectly capable of writing this code in Haskell. And note, you can't do this with interfaces. Questions so far? So to sort of broaden our viewpoint for a moment and just talk about the trade-offs between type classes and object-oriented interfaces. So type classes are nice in a number of ways. So one is that they can do multiple constraints very easily. In Java, if you want to take in a thing that knows how to show and knows how to EQ, well, you can't really easily say, hey, this object needs to implement two interfaces, right? Normally you just say, okay, I have some comparable thing, or, oh, I have some, I blah thing. Technically you can. There's a very advanced feature in Java called f-bound quantification that lets you do that. But in Haskell, slapping on multiple constraints is very easy. It's very intuitive. It's so easy that the compiler can figure it out automatically for you. You just slap on extra constraints onto the type signature, no problem. Another great thing about type classes is you can retroactively give instances to types. So remember the question earlier in lecture, where someone asked, where do I define instances, with the type class definition or the data type definition? If you think about interfaces, interfaces can only be defined to work on a type when you are defining the type in question, the class in question, right? You have to write the class and then implements and then all the interfaces you know about. If someone else later comes up with some new interface, you're kind of out of luck. There's no way to retroactively add it without actually editing the class in question. But in Haskell, that's very simple, right? Instances can live wherever you want. So when you define a new type class, you can go ahead and add implementations for that instance to all of the standard library types, which you normally wouldn't be able to edit directly. And finally, Haskell has no subtyping. So this makes some things easier to do, some things harder to do. When we write a addition function in Haskell, things are sort of easy for us in one sense because we don't have to worry about like losing the precision of the subclass. We can just say A to A to A, and we know if you give me a bunch of integers, I'll give you back out an integer. And that's quite troublesome when you're in Java because you sort of lose information when you pass in a subclass to a interface that is doing a binary operation. But then, we don't get to do fun stuff like, doing... there's stuff that subtyping lets you do that we can't do in Haskell, and so Haskell says no subtyping. There's a question in chat, which is some of these possible features seem possible in languages like Swift with protocols and extensions, and they ask if they're still value-based dispatch. Swift is a funny example. I don't actually know how Swift protocols and extensions work, so I can't compare. One thing that I will say is that since when type classes were invented in Haskell, they made their way out to lots of programming languages. So you might see something that's very type class-like, and in fact, it is type classes. So they're a very useful tool, even in object-oriented programming languages. Just a little bit of a fun slide. So type classes were added to Haskell in 1989. They were considered a new and radical feature, but they had to do it because they really needed equality to work in the language. But since then, type classes spawned an immense series of research and further directions. So You saw me add that language pragma for instance SIGs. Well, if you start like playing around with type classes and doing things and thinking to yourself, I wonder if this works. Well, chances are GHC will say, yeah, this does work, but you have to add a type classic, a language pragma to do it. And because there were tons of like things that they thought were like kind of, edgy, kind of, not entirely clear if they were warranted or not, but we implemented them and they ended up being useful. So for example, I've shown you all only examples of type classes that take a single type variable. But what if you wanted a type class that had multiple type variables involved? Well, that's called multi-parameter type classes, and they were invented in 1991, and so forth and so forth. There's tons of fun stuff. And so, in fact, one would say the culmination of type classes has been in so-called dependent Haskell, where we can actually do type level computation on terms. I'm not sure what my bonus lecture is going to be about this year, but one of the rotating topics is dependent types. And so at the very end, you can learn more about that. So tons and tons of applications, very, very deep. I'm not going to get into all of them, but like you can go really far with type classes in Haskell. So just to summarize, type classes, Simon Peyton-Jones would say they are the most unusual feature of Haskell's type system. Most of the other things we've talked about were already seen in languages like ML and other functional programming languages that had type inference. But type classes, those were very special to Haskell. And, originally they were just added to solve the equality problem, but it turned out they were really flexible. And so there are tons of extensions you can add to type classes, and type classes have been a huge influence on many other languages. And the two that I do want to call out explicitly here, Rust is this cool new systems programming language, and Rust has a system called traits, which are basically type classes. Like if you know how Haskell type classes work, you know how Rust traits work. Another is in C++. If you are in C++ 23 or like some similarly futuristic version of C++, there's this thing called concepts, which helps solve some problems from template-oriented programming. And concepts were basically a bunch of people, including PL researchers, who are like, how can we deal with the monster that template type checking is? And they took a lot of ideas from type classes to make it work. Okay, so that's all of the program material for Haskell type classes. I have less time than I thought I would. Are there any other questions? I think I'm just going to do questions at this point. While you're thinking about questions, I have released the next homework. The next homework has two parts. The first part is type classes. You do dictionary passing style in that homework. And the second homework is about monads, which we're going to cover on Wednesday. The homework is not due on Monday because Monday is a holiday. You get until Wednesday to do it. So you also have some time. Questions? Okay. Thanks, everyone. See you all on Wednesday.